Good morning. So first speaker this morning will be Steffens. I'll be talking about global BD, formalism, and derived geometry.
Should I take it away? Should I wait a little bit? Or?
Go ahead, please.
All right. Yeah, so thanks to Stefan, Pavel, and Chris for organizing this wonderful thematic month, 3 weeks. We appreciate the invitation. Yeah, a global BD formalism. Let's see if we get there today. Okay, this is the setting. So M for now is a manifold, which you understood is closed. And let us say that E is a system of nonlinear PDEs on M. It's a bit vague for now, but I'm going to be much more specific about what I mean by this in due course. And I want to talk about this morning, this hour, about this object, the moduli space of solutions of E. So the question I want to ask is, what kind of mathematical object is this? Okay. Yeah, if my handwriting deteriorates to a point that you can no longer read what I'm writing, then someone should stop. So to make this maybe a bit more concrete, so say like E is like something like one PDE that acts between vector bundles. So suppose if E and F are both vector bundles on M, and P is a PDE, nonlinear of some order, then this could be, for instance, the zeros P. Maybe there's a group acting. Maybe it's an infinite dimensional group. We don't know yet. We can look at this. This Gaussian space. And we ask this question: what kind of thing is this? And what we notice, here. So this is not a map. Because so problem 0. Suppose that P is the zero map, then the zeros of P are all of the sections of E. So this a priori an infinite dimensional object. And even if this set of zeros were finite dimensional for some reason, what we're still doing is we're taking the zeros of a function, and if P is a function that is not transverse to 0, right? This object is generally not a smooth manifold. So P could cut out some very ill-behaved space, something like a Cantor set or something. And so we might have infinite dimensional transversality issues. And moreover, this group acts in a non-free, non-proper way. This also introduces singularities of this object.
Sorry.
Yeah.
When you say Cantor set, you mean it, or it's a figure of speech?
I mean everything I say. Right? No jokes will be told.
So what is the example?
I'd have to think of it. But you could definitely cook up something finite dimensional, and you could for sure cook up something.
It's not a very typical.
No, that's right.
It's generic topological spaces can set.
Yeah, but in that case.
You can cook up pretty well PDEs. But that impose lots of conditions to sort of.
A solution to a generic equation is often never a Cantor set.
That's true.
Do you mind writing a little bit bigger? Sure, thank you. So I want to now talk a little bit about sort of two approaches, two ways of dealing with this object. One of which you've seen probably this week and week before, one perhaps not. And both sort of involve tweaking this thing, sort of changing this object, making it a bit simpler, a bit more attractive. So one thing we could do is, well, let's do that over here, is we could pick a point P in this thing, where we pick an entire submanifold. So this is a smooth manifold. And what we can do is we can look at a simpler space that I'm going to denote like this. This is the formal neighborhood of P and X, maybe N. I'm not writing bigger yet. We'll get to it. And this object is, so this is by general principles of derived deformation theory. But this object, this object is, this is a DG Lie algebra, or an L infinity algebra. And this DG here sort of has to do with these two sources of singularities. So DG here means that we resolve these two singularities in a homological fashion.
You meant that you can take a point or a sub. What is N?
N could be a smooth manifold. So let me. So this is for P, and for N. So instead of a DG Lie algebra, we get a DG Lie algebroid over N. So these are objects that control the formal neighborhood of either P or N inside this thing, whatever that is. We don't know that yet. And if actually this system of PDEs actually comes from something like the Euler-Lagrange equations of an action functional, then we're in the setting of the classical BV formalism, as you've probably seen in class many times. So if E is actually something like the Euler-Lagrange equations of an action, then this is equipped with, so this gets a degree -1 non-degenerate pairing. Also known as a shifted symplectic structure. And one other way to say that is that you can cook up an enhancement of this action, something called SVV, the VV action, that knows about the DG Lie algebra structure, as it's the Taylor coefficients of this object know about the structure coefficients of this infinity algebra, and the fact that these structures are compatible. That's something that is called the classical master equation. So that this is just one way of saying that. This is just one way of saying what a shifted symplectic structure on a DG Lie algebra is. Right. So many names are attached to this. So primarily Butlin and Dolkovitsky. Nowadays, the names most associated with this are, I guess, people in this room like Pavel, Alberto Cattaneo, Collier and their descendants, and maybe Kevin Costello or William and their descendants. So another way to approach this object is to do something slightly different. What you could do is, instead of looking at this possibly badly behaved map P, what you could do is you could tweak it a bit to make it better behaved. So instead of looking at P, we're gonna change P to some P plus epsilon. So what this does is this fixes one. So and then under some assumptions, so let's say that we assume that, so M is closed, in particular it's compact. And if we also assume that P is an elliptic PDE, then some magic happens, then actually this object, this is a finite dimensional manifold. Right, so if under this condition of ellipticity, P cuts out a finite dimensional subspace of this space. So this is what people do say in gauge theory. These are, say, instanton moduli spaces. Cyber theory, for instance. And in symplectic topology. So then you're looking at various flavors of pseudo-holomorphic curves or disks or strips inside some symplectic target. Let's call it Y. All right, so both of these approaches have their pros and cons.
Sorry, but are you allowing possibly stratified spaces or?
For the moment, no. But maybe might at some point. What do you mean stratified?
I'm saying if you have a group action, you still have stuff to check, right?
Yeah, so I mean, in this is a bit sloppy. So in the case of a gauge theory, so you don't generally get a finite dimensional manifold. Maybe you get an orbifold broadly groupoid. So yeah, you still have this problem too here maybe.
Just to make sure I get the notation, so the sol means the quotient of the zero set of P modulo the gauge group, or it means the zeros of P?
So sol is whatever I'd like to be at any given time. So yeah, so
Context dependent.
yeah, exactly. So solia is if there's symmetries, it's the moduli space modulo symmetry. But yeah, this will become more precise in a bit. Yeah, so obviously,
You might not want to write on the stationary board, pull up the movable board from the bottom.
yeah, that's right. Thank you. Am I doing that right? So these both have their pros and cons. So here, a pro is that we don't do this modification of this operator, right? So we manifestly we have all the symmetries, all the structures that the original equation had. And so if we perturb something, then so we start with maybe some Lagrange PDE. We perturb it a bit. There's no guarantee that it's still an Lagrange PDE. So you might get the shifted symplectic structure if you do something like this over here. So that's the downside here. So we're changing P, we're changing the equation. So we only talk about the moduli space up to cobordism in this perturbation picture. So con here is a con on this side, of course, is that we only see a very small part of the moduli space. We only see formal neighborhood. And of course, on this side, we do see the whole space. So what I want to primarily do today is I want to introduce when introduce a formalism that somehow is the best of both of these worlds. Which is going to be a variant of derived algebraic geometry as developed by Jacob Lurie and Jonathan Susi. And this is going to be called derived differential geometry, derived C-infinity geometry. So what we're going to do today is like explain what this is. So once we've done that, we have to come up with some way of arguing that these things sort of even away from some formal neighborhood and non-perturbed, how these global moduli spaces naturally are objects in this setting. And then, well, once we've done that, we could sort of try to play this game over here. So we could try to shift with symplectic structures on these moduli spaces. Maybe we want to be very ambitious, do something like non-perturbative colonization. We would like to, to have access to this entire moduli space. And that will require something that I will call a global BP formalism. Global in the sense that we're away from some formal neighborhood. So maybe I will note that for the rest of the talk, we're going to be dealing with we're going to have lots of DG objects, lots of derived objects. So to deal efficiently with things like this, we're going to be in the setting of infinity categories. And for me, like I'm a very down-to-earth person, so for me, an infinity category is a simplicial set that satisfies the inner horn lifting. So we replace the category of sets by the infinity category of spaces, which will not look like an S, but that's what it is. Any questions so far? Excellent. Okay. Which is the
other side works more effectively
Okay.
in my mind. Yeah, I would just ignore that. The other one is better.
this one over here?
The other side. The other side of that.
Okay. This is much better now. Whoever wrote this was not lying. Okay, so maybe some of you are already familiar with what objects in this theory are. If that's so, then that's great. This is one of the times where you can start looking at your phone. But I will assume that most of you are not. That a critical mass is not. So let's just go through this. So I'm going to give it a non-standard definition of a commutative ring. So a commutative ring is, say, it's a commutative algebra over, say, field K is a functor from a category that I'm going to call poly K into sets that preserves finite products.
What is that?
That's what I'm going to write right now. So poly K is
I just cannot read the letters.
oh
E.
Wholly. Yeah. So for reasons that will become clear in like 3 seconds. So the objects of this category are all affine K spaces. And the morphisms are polynomial maps. I'll mark them. So why is such a functor a commutative algebra? Well, right, there's two, of course, obvious maps from A2K to A1. So there's addition and there's multiplication. And by functionality, they induce two maps like this. Right, so I can take the 2 out because F is supposed to preserve products. That I'm also going to call addition and multiplication. So functoriality tells me that the image of A1 under F has a commutative and associative multiplication and addition. And similarly, there is a unit, and sending F to F of A1 with this particular structure of commutative algebra, that's an equivalence of categories. And so this one nice thing about this.
Why is this a K algebra? Like where?
Because we're doing affine spaces over K.
Yeah, but like where does the scalar multiplication come from? Let's see it. So,
Sorry?
like f of A1K must have a scalar multiplication, right, by K. It's like
If you're going to talk, could you speak up? Nobody can hear you.
So that not A1 to A1, that's just multiplication by a
Right.
scalar. And precomposition gives you.
Oh, okay. I was asking where the scalar multiplication.
Yeah, I have no doubt, but I mean, don't mumble if you're asking a question.
Thanks for the advice.
Yeah, pleasure.
All right. So the nice feature about this definition is that it carries over very nicely to the infinity categorical setting. So a derived commutative algebra is the exact same thing. It's a functor from poly K to spaces that preserve finite products. So now it's a functor of infinity categories. Which has the effect that now associativity and commutativity are now satisfied up to an infinite sequence of higher coherent homotopes. And so this you can show that this infinity categories, let me call it the commutative algebra. This has an operatic description as, so say that the characteristic of K equals 0, then this is the same thing as E infinity algebras in connective K modules. So this is the basic. This is the basis for doing derived algebraic geometry. We want to be in. We want to sort of enhance our rings with some sort of smooth structure. And now an obvious way of doing that stares us in the face. So what we could do is just replace the category poly K with the following category. The category of Cartesian spaces has objects, all Cartesian spaces, and morphisms, all smooth maps. So then a functor preserving products is something in the spaces gives me an infinity category that I'm going to call derived to infinity algebras. So notice that poly R sits inside here as a subcategory. So in particular, there's a restriction functor. So any derived C infinity algebra is in particular a derived commutative algebra, but it has more structure. So for any smooth map from Rn to Rn, there's an induced map on whatever the value of f on R1 is. I don't know. All the smooth maps that, they sort of that the functionality in all the smooth maps gives me like a very rich algebraic structure on this side. So a non-example of a derived C-infinity algebra is a power series ring. And this you cannot give this a structure of such a thing compatible with this algebra structure. An example is, say, smooth functions on a manifold, or smooth functions on a manifold divided by any ideal. Okay. So, and I've told you like what the basic infinity category on which we're going to base our theory of derived differential geometry is going to be.
Sorry, but the power series ring has a series structure.
Yeah, but this is the this is the just the ring of polynomial. Yeah, so this another example is this one is not, but this one is. So now we're just going to like follow algebra geometric paradigms.
Why is it an example? Why are the power series an example of this?
Because if you have a smooth function, you can take a Stator series that will produce a map.
And so
I've also told you now. I've also told you that if you take smooth functions on a manifold and divide by any ideal, that is an example of such a thing. So what you can use, you can take smooth functions on Rn and divide by the ideal of functions. Let me write it like this. So this is the ideal of functions that are flat at the origin, that have all of their derivatives vanishing at the origin. And that is precisely this way.
okay.
Very good questions. But yeah.
So all those are examples where the structure is actually just determined by this boundary that R1. Can you give an example where you actually need the higher? Like the smooth functions on M, you can determine the smooth functions to Rn. Right?
Yeah.
Give an example of that.
It's product preserved,
Yeah,
I think we know.
Up to equivalence. If you restrict to just the subcategory that contains R1, you don't get the full data of a general object in the second category. Or are you taking like strict products?
I mean, it's a product preserving function of infinity categories. So that like the strictness has nothing. Just come talk to me afterwards. We can sort this out. Whatever your question is. Yeah. So we have our rings now. What do we do? Well, now consider the following functor. So this is the category of topological spaces, and it has a functor to the infinity category of large infinity categories. What does this functor do? It sends the topological space X to the infinity category of sheaves on X with values in derived C-infinity algebras up. There's also an up here. Right? If we have a map from X to Y, there's a pullback of sheaves. So it's contravariant. And then by general categorical construction, due to Grothendieck in the one categorical setting and due to Lurie in this infinity categorical setting, for any functor from a category up to infinity categories, you can cook up a functor, an infinity category over top. So there's something sitting over top that's going to go top. It's called top C infinity, whose objects are pairs of a topological space together with a sheaf of such things. Just as in algebraic geometry. And inside here, we have a subcategory of locally ringed objects. So what you demand is that, of course, for all X and X, the stock of the structure sheaf is a local ring. Plus, in this smooth setting, you don't just demand that the ring is local, but you also demand that its residue field is R. So you demand this ring has a pointing.
So this forgets this, the smooth stuff, doesn't it? Like here you look at this as a ring, I mean, it's smooth.
I mean, when I say local, I mean local as a ring. Yeah. But like you can think about what it means to be local. So there's a, this is somewhat ad hoc, but there's a sort of a much more sophisticated way you can think about locality of ring spaces. And if you do that in the smooth setting, what you find is that the correct notion of locality is these two conditions. Right. So the ordinary category, can people see if I write here? Yeah, okay. Am I writing big enough, Stefan?
It's better than it was at the beginning. A little bit bigger might be good.
I'll make an attempt.
Wait, I have a question. So.
Yeah.
In this setting, by local ring, like, are you passing to the pi naught level to detect localness? What do you mean by a unique maximal ideal?
I mean, like I said, like there is a way you can think about locality in a sophisticated way which turns out to mean locality on the pi naught level. It's something you should improve.
Is there a connectivity hypothesis on your E infinity?
I mean, these are automatically connected. So that's the.
Oh, right, they're
That's it, when you go in spaces.
preserving the spaces. Okay, thank you. Thank you.
Yeah. So the ordinary category of manifolds sits fully faithfully inside here. Just of course, by setting a manifold to this pair. And one should note, so what is the reason for doing this instead of, like, why shouldn't I just take this object as a ring space where I just think of this as a ring of ordinary algebras and I just forget all this extra smooth structure here? Well, the following goes wrong. So this functor will send the product of of two manifolds to the product with the product of with the sheaf being the smooth functions on the product. But this is false if you work in the algebra geometric variant. Like you don't get this ring, but you get instead C infinity M. And these are not. So what this formalism does, it sort of categorically does some kind of like topological completion of this.
What's the subscript under that tensor product?
R.
So, sorry, could you just repeat once again what you've just said?
Yeah.
What are the two different? So one is non-completed, one is completed.
Yeah.
So yeah.
Yeah. So this sort of so this category here, this infinity category has all limits and colimits. In particular, it has coproducts, right? So the coproduct in commutative algebras, that's the ordinary tensor product. But here the coproduct is something else, right? And it has the property that if you take two manifolds, it's smooth function on two manifolds, you take whatever the coproduct is here, you get smooth function on the product. So if you take Rn and Rn, that's completely tautological. For manifolds, you have to do a little bit of work, but it's still true.
Okay.
And moreover, so more questions now? Moreover, if you take a pullback diagram, so this is a pullback diagram of manifolds, and you suppose that F and G are transverse, then this is carried to, so this is also a pullback in here. But even if we're in a situation, so suppose that F and G are not transverse, then we can still take this pullback in this infinity category. So there's still an object Q OQ, which has the correct intersection theoretic information if it remembers the right amount of information as sort of as Q coming from intersecting manifolds M and N in P. So that's what this infinity category achieves.
Saying that this function preserves limits.
This function, no, it only preserves transverse pullbacks. Preserves products and it preserves transverse pullbacks, but it does not preserve arbitrary limits of manifolds because the manifold doesn't have arbitrary limits. So that also, so it could be that F and G are not transverse, but that a limit exists.
Okay.
Even in that case, this limit will not be preserved by this function. So it's actually preserved if and only if it's transverse.
So this Q would be typically called like the derived intersection of the
Yeah,
manifold.
that's right. Sorry. Now we can define a category, now we can define an infinity category that we call derived C infinity affines. And this is just going to be like arbitrary finite limits of manifolds in here. And now, since we're working with these structured spaces, we can just glue these together in the homotopically correct sense very easily. So now this is this is exactly analogous to the infinity category of affine derived schemes for finite presentation. And an arbitrary scheme is a gluing of such things. So there's an infinity category of derived C infinity schemes. So both of these sit inside here. And this is these are pairs of this form, right? So this is something like this that locally looks like something like that, right? So it has a cover by UI such that UI. Oh, actually, triggered the UI is something that sits in this subcategory.
Sorry, what is written in on the first line?
Here.
Yes.
So this manifolds don't have transverse intersections. So what we can do is we can just, but this category does have all finite limits. So what we can do is just take an arbitrary finite diagram of manifolds, think of it as a diagram in here, take the limit. That's gonna, by definition, give me an object in the category that I denote like this. Right, so these are sort of somehow formal intersections of. So in particular, and again, it's not a joke. The underlying topological space of Q could be a Condor set, but then sort of all the information about this object is contained in this structure sheet. Before we move on to sort of more exciting things, so there's a much more general way of gluing these things together. So let's say that a functor of this category of affines in spaces is a sheet. If the value on any such pair, you can recover it as the value of, so suppose we have an open cover of X, then I can recover the value of X of X as the values of all the UIs of X sub UIs plus some gluing data. This gives me a very large infinity category of sheaves. We call this derived C infinity stacks. That's sheaves on affines. And I just want to note there's two natural subcategories in here. So I can just play the same game for the smaller category of manifolds. So that gives me, turns out that like the category of smooth stacks, that's sheaves of manifolds, sits fully faithfully inside this category of derived stacks. So this looks like it's completely formal and trivial, but it's actually not. You have to work a little bit to prove this. And this category of derived C-infinity schemes also sits inside.
Well, Pelle, I have a silly question. So classically, it's fairly easy to give examples of schemes that are not affine.
Yeah.
Do you have a favorite simple example in this derived C-infinity setting?
So it turns out that like in the C-infinity setting, many more things are affine than in the. I mean, so it turns out that sort of to be affine, it suffices that the underlying topological space is paracompact Hausdorff, and the structure sheaf satisfies, and sort of the topology of X is you can get as open sets by bump functions in OX. That's actually true for like an enormous class of space. It's actually very hard to come up with something does not sit in there.
But anything infinite dimensional won't be affine.
Sorry?
And anything infinite dimensional won't be affine.
I mean, that's right. Not in this sense, like because I mean, if so, there's so here I've sort of secretly affine means finite presentation.
But that's a very like ind example.
Yeah.
Like classically, you don't need to pass the ind to give something that's
Right.
affine.
So and lots of infinite dimensional manifolds, they are affine in the sense that like they can be recovered from if M is an infinite dimensional manifold, this is an object in here, and you can completely recover M as and its smooth functions, given that M is compact and has this property that it has enough bump functions. So what you can do is you can take like the hill, like you can take like an LP space for P odd. That will not have enough bump functions, but for P even it will be. I don't know if you like that example. Something you can do.
The long line would also be like from your.
Yeah, like if you get rid of these paracompact Hausdorff conditions, then. Yeah, so in fact and I just want to say about this embedding, you can characterize the image, sort of an object, throw in a stack, sits inside here, if and only if you can find a cover of X by open substacks. So if X admits cover, an open cover by affines. Because if you have an open cover by affines, the maps into X give you gluing data, and in this category of derived C-infinity schemes, you can do this gluing, and that will give you back X. This looks a bit stupid and tautological, but this is actually very powerful, as we will see right now. Yeah, more questions?
What's X a priori in the statement?
So X is an arbitrary functor that was called F here, from this infinity category to the infinity category of spaces that satisfies this gluing condition. So this is an enormous infinity category, and this is a representability criterion. Like it says, if you can find a cover of X by affines, then it must itself be affine. This will be useful in like. Okay. Okay, so let's get back to these modular spaces. So now I claim that this thing here, this is naturally. So this is the reason to actually, why would you introduce all this formalism? The reason is what I'm writing now. This is naturally an object in this category of derived C-infinity schemes if M is compact and E is an elliptic system. So I'm telling you that if you define this modular space in the right way, you can give it a structure as like a homotopy coherent gluing of a collection of objects you get by intersecting manifolds finitely many times. So how would you do that? Well, what you could try to do is construct these local models of this object by hand, and then constructing the gluing data by hand. And this is actually in gauge theory and symplectic topology. This is how people would go about doing that. So that you would have like a modular space of pseudo-holomorphic curves of some flavor that you could not write as a manifold, but that you would write as an intersection of a non-temperate intersection of smooth manifolds locally, and then people would start. There would be an open cover of this space by such spaces, and then you can try to introduce enough coherence data that you can glue all these local models to a global object. That's very arduous. So we're not going to do that. What we're going to do is we're going to follow Notre. We're going to do this in 2 steps. Step 1 is we're going to locate this object inside first in this very large infinity category. And then we're going to apply that criterion. So we're going to apply the fact that I can detect whether or not something lives inside the subcategory of schemes. Locally. So this has the upshot of like, once I've done this, I've already given this space all of the smooth structure that it could possibly have. Yes.
So by your star, you have X in the category of stacks. Did you mean to write schemes there? Did
I not write it?
Is that X is in C infinity stacks.
That is yeah, that's this statement is not correct.
Scheme if X exhibits.
So a priori X lives in here. If then X lives in the subcategory. Yeah. If and only this is true. Is that
Given a stacks and F
You
line.
wrote the same thing twice.
No, I did not. So
Looks like ST and.
Yeah, that's SCH.
Okay.
that's just because I can't actually write. That's the thing.
Your letters help.
You keep insisting. Is that clear?
Yeah.
All right, great. Yeah, so actually let me state a more precise theorem than I've been doing so far. So it turns out that like this step, this is really easy. So suppose that Y over M is a fiber bundle. Then, well, I mean, given a fiber bundle, I can make an infinite dimensional manifold of sections, right? I can look at the set of all sections and then try to give that thing some kind of topology and then some kind of smooth structure. That space of sections you can define much more naturally in this very large infinity category of derived C infinity stacks. So what you do is, so if there exists a stack called sections of Y to M. So to say what it is, so it should be some sheaf on this category of affines. So I just have to say what it means to map into this space, and by that I declare to be just a map So just an XOX parameterized family of sections, which this diagram commutes. So this is just the obvious first projection. This is the map I saw.
What's that? YX. What it's no that thing. I don't understand.
Here?
No,
This?
it's Y times X.
Yes. So what do I do? So what does it mean? So I'm just going to tell you what does it mean to map an XOX, an object in that category of affines. What does it mean to map into it? By your data, that's the same thing as specifying its value, specifying the value of the sheaf on this guy. I just declare that to be a commuting diagram like this. And so if y is a point, so if XOX is 1 point, then I just get one. That's just one particular section. So if I vary this thing here, then I get like a smoothly parametrized family by this derived object. Right. Why is it? The arrows go the right way. You agree that they do? Okay, right. So one can show, it's a little bit of work, but you can do it. But if you give yourself, so say P, so P is a nonlinear PDE. Say from a sections of.
I'm sorry, I'm also confused by your statement there. Like, suppose we just have one section, which means if X is a point, right?
Yeah.
If X is a point, you would get a map from M to Y as a section, right? So I don't see a map from M to Y. I think it should be M cross X comma GX into Y, right?
Yeah, this is right. Yeah.
Okay, now I'm happy.
The arrows did not go the right. You should have objected more.
I just want to.
I mean, the arrows go the right way, but just the objects did not. We are both there. Is it clear what's going on? So, given a nonlinear PDE from sections of, say, Y1 to Y2, you get an induced map between these stacks. So here's a theorem. Let's suppose you have 3 fiber bundles, say Y1, Y2, and Y3. And you're given PDEs. Say P and P prime. What you can do is you can take a pullback diagram. So let me call let me call the system P prime. Let me call that now B. But you can take this pullback diagram in this very big infinity category of stacks. And if so under the assumption that M is compact and closed, and this system, so P1 and P2 are jointly elliptic. Then actually this object lives inside this subcategory of scheme. So actually what you can do is you can find a pair Y or Y that is locally looks like something intersected, so that two manifolds non-transversely intersect in a third. That is just going to be equivalent to this thing. And this is not so easy to prove. So you find these local models. So this is locally something like the intersection of two manifolds in a third, or maybe the zeros of a vector bundle, of a section of a vector bundle which is not transverse to zero. And you find these local models by doing like some heavy duty nonlinear elliptic Fredholm analysis, together with some Topos theory to make sure that all of this works in this setting where you're not referencing any analysis. I'm happy to talk to anyone who wants to hear how this is done.
Sorry, I don't understand the equations. So P is going from y1 to y2.
Yeah.
And P prime from y3 to y2.
Yes.
So what does the sol M mean?
It is whatever equalizes P and P prime.
How should I think about? Is there like the?
Well, let me give you an example.
Yeah.
So what you can do is say we're doing say flat connections. So this is slightly outside of the scope of what I just said, but the theorem still holds. So what you can do is look at this the stack of connections. So let's say M is a three manifold. G is a compactly group. And P is a G bundle. Then you can look at the following thing. So the stack of connections on G, on P, modulo gauge. This is something you can construct in this big infinity category. And the curvature map is a nonlinear second order PDE that lands in the stack of two forms with values in the adjoint bundle. And to be flat is just demanding that this is equal to 0. So the stack of flat connections on P is whatever sits in this pullback diagram. You clear what's going on? And so if I take a pullback of two things and a third, I'm asking, okay, when is something in here zero in here? And the sort of a variant of this theorem where you also have symmetries, in this case gauge symmetries, tells you that, well, this object is not going to be representable by something of the form y or y. So this is like something which is locally the zeros of some smooth function. But this is going to be locally something like the zeros of a function modulo a compactly group. H is going to be the stabilizer of the gauge group at one particular zero.
So is this an example of something which is not affine, or is it affine?
Yeah, so this is not affine because so this is not something you can construct as a pair of a space with sheaf of rings. So this is a more kind of, so in algebraic geometry these are called Artin stacks. So this would be an example of like a derived Lie groupoid. Yeah, so I'm actually going to leave it at that. I've run out of time, but if you want to hear about the title of the talk, I suggest you come talk.
Thanks very much. Questions, comments?
So, can you, how dependent is this on the fact that you have a group action, for example? Can you generalize that? So here you say I have connections modulo gauge. Can you look at examples where
you have a groupoid
attribution which is not evolutive except on the zero?
So yeah, so this theorem over here, well, like I said, you invoke some heavy duty analysis, right, to get these local models. Here you do more analysis, so you don't only have to get a local model, but you also have to find a slice for the gauge group. And I'm not sure how to do that in kind of generalized setting.
The DB formalism was sort of intended to handle situations that go beyond practical.
Sure.
Is that something that is faithfully represented?
Let me pessimistically say no. At the moment, no. I mean, like you can write these things down, but like these sort of representability theorems, I think, are generally out of reach in those kind of situations.
So this last example you gave, being a little unhistoric, Axelrod and Singer showed that its completion, if you like, the BV structure underlying it, is a AKSZ AKZ model. I wonder if you can, in this construction, can you see any relic of the statement that this is
That's very good, because now I have like a good segue into talking about like what the rest of the talk was supposed to be about. Like so this is like not the right kind of, so this is a derived object, so it's like the zeros of something non-transverse modulo compactly grouped. But the tangent complex of this space that you know we should be looking at like the derived critical locus of the term sinus functional, and we expect this to be like a 4-term complex shifted by 1 degree, where the bearing is integrating with the contact interval. But on this local model, you don't see that. You only have a 3-term complex here. You only see the fields and the ghosts and the anti-fields. But this object does not see the anti-ghosts. So instead of looking at this thing, so you should look at something like, so if these are the fields and the ghosts, you should look at the cotangent of whatever this is. We call this whatever y, and map 0. This should be the differential of the action. And then this is symplectic, so this should be -1 shifted symplectic. But here you encounter a problem, because this is some sort of infinite dimensional stack. You have to make sense of what is the cotangent of this thing, and that's the way to resolve that is to sort of be somewhere in between this finite dimensional picture and this infinite dimensional picture. You should work with instead of C-infinity algebras, like C-infinity algebras internal to D modules. Instead of your free object should be like infinite jet bundles instead of smooth functions. And that's a setting where you can define this.
But to make it look closer to AKSZ, like shouldn't you maybe have some mapping stack of like M into some Dorami version of?
So it turns out I'm talking about these systems of PDEs all the time, right? So what is a system of PDEs geometrically? It's something that lives over the de Rham space. So any system of PDEs is actually, if you do this correctly, if you don't do this in an ad hoc way, but think about a PDE as a geometric object, it's something living over the de Rham stack.
Maybe I'm just saying that capital Y could be rewritten to make it more transparent.
Right. And the solution space of E is just the space of sections. So in this sense, every field theory is an AKZ theory over its de Rham space.
Maybe 2 completely different questions. So there's I see
no, they have to be this. They have to be this.
2 assumptions in all of this. So the first is it's always an elliptic system, right?
Yeah.
So always in the right side of the initial picture.
I mean, you can define these. You can define this object sol M of E for any system of PDEs, but you only get this this representability theorem for elliptic systems.
There's no whole of it.
No.
And the same goes for M being closed.
No, you can do M could be compact with boundaries, and you impose elliptic boundary conditions, or M could have like cylindrical ends, and you impose like decay, like exponential decay. That's something you could do. That's something you should do if you want to generalize this to moduli space of broken. If you're doing Gromov-Witten theory, you have like nodal curves. If you're doing the Kai category, you have broken strips. That's the kind of setting.
So if you have a manifold with boundary and so you have an elliptic complex, do you need to have the boundary conditions also be adjusted so that you get a Fredholm operator? Otherwise, things don't work.
Otherwise, if you don't have Fredholm operators, you use many times like elliptic regularity and like nonlinear elliptic bootstrapping to get these little things.
All right, well, let's continue this discussion upstairs and let's thank Pelle again. Next one is at 11.
Reading of the